Topic 1.2 Collision Theory. In this subtopic, we are going to focus on concept of collision theory, the term involved activation energy, and what is transition state theory, and lastly, you should be able to draw energy profile diagram of a reaction.
Collisions happen when two or more objects come into contact with each other and a transfer of momentum and kinetic energy occurs. Collisions occur every time you hit a baseball, bounce a basketball, or play pool. When objects collide in the absence of external forces, they form a system in which the net momentum of both objects before the collision equals the net momentum of both objects after the collision. There are two types of collisions: elastic collisions and inelastic collisions. An elastic collision is defined as one in which no kinetic energy is lost, no damage is done to the objects involved, and there is no generation of heat. In the real world, no collision is perfectly elastic because so many other forces come into play, like friction, air resistance, and gravity. However, the game of pool offers a fairly good elastic representation. Pool tables and billiard balls are designed to reduce the effects of friction, resulting in close to ideal elastic collisions. When the cue ball hits the resting 8 ball, it sets the 8 ball in motion. Having transferred all of its momentum and kinetic energy, the cue ball comes to a rest. The net momentum of the cue ball before the collision equals the net momentum of the 8 ball after the collision. Momentum and kinetic energy are transferred and conserved. If the 8 ball is already in motion when a similarly moving cue ball collides with it, then the 8 ball will gain some of the initial cue ball's momentum, and the net momentum before and after the collision will be conserved. If the 8 ball and the cue ball are traveling at the same speed and collide head-on, then they will bounce off of each other with the same momentum, but in opposite directions. Their momentum and kinetic energy are transferred and conserved. The second type of collision is an inelastic collision. In an inelastic collision, momentum is still conserved, but kinetic energy is lost in the system, resulting in the creation of heat and damage done to the colliding bodies. Bodies that are involved in an inelastic collision end up entangled with each other or stuck together.
In a chemical reactions, reacting molecules collide between them. When more collisions occur, meaning frequency of collisions per time increase, the rate of reaction will be increased. Only effective collision can cause a chemical reaction. What is effective collision? When molecules collide, total potential energy must equal to or greater than the activation energy, and the molecules collide at correct orientation. The meaning of activation energy stated in the slide before is the minimum energy required to initiate the chemical reaction. From the graph, activation energy is measured from minimum energy of reactant until maximum peak of the curve. Collision at correct orientation can be illustrated by this equation. When collision between molecule of nitrogen monoxide and molecule of ozone occurs at correct orientation, it will produce a new product. When collisions occur at wrong orientation, there will be no new product formed. So, two requirements for effective collisions are: the molecules must have enough energy and they collide at correct orientation. Transition state theory. Transition state is a state when a chemical reaction takes place, reacting particles collide with each other and form unstable structure before forming a new product. At this state, a species formed is called an activated complex. The activated complex resulted from an effective collision where the old bonds are breaking and the new bonds are forming. It can be decomposed into product or reactant. So, activated complex has these characteristics. It is very unstable and has a short half-life. Its potential energy is greater than reactants or products. The activated complex and the reactants are in equilibrium and it decomposes to form products or reactants. For example, an activated complex formed when effective collision between two molecules of nitrosyl chloride occur to form new. The old NCl bonds are breaking and new Cl2 bond is forming. The activated complex decomposes into products or reactant. The energy involved for this reaction represents by the energy profile diagram below. The reactant nitrosyl chloride has a certain initial energy. In order to form products, energy is absorbed. Activation energy is the minimum energy required for a reactant of nitrosyl chloride to be converted to product. The energy of activated complex must be overcome, thus the reaction is endothermic.
In this video, we are going to look at exothermic and endothermic reactions. So what are they? How are they different? What about their energy levels? In the next couple of minutes, you'll know everything you need to get started. An exothermic reaction gives off energy to the surroundings, like this fire giving off heat. Whereas an endothermic reaction takes in energy from its surroundings, like this poor melting snowman taking in the heat. Just remember, exo means external, so giving out, and endo means internal, so taking in. Let's start by having a quick look. Because exothermic reactions transfer energy to the surroundings, and this energy is usually heat energy, they cause the surroundings to heat up, just like a bonfire, keeping everyone warm. Other examples of exothermic reactions are the neutralization reactions between acids and alkalis, the reactions between water and calcium oxide, and respiration. It is easy to detect exothermic reactions. Just get your thermometer and see if the temperature increases. Watch the hydrochloric acid and sodium hydroxide solution being mixed and see how the thermometer increases. Most chemical reactions are exothermic because heat is given out. Physical processes can also be endothermic or exothermic. When something freezes, it goes from liquid to solid. Bonds need to be made for this to happen, and to make bonds, you need to do some work. Thus, energy is given out and freezing is exothermic. Similarly, when condensation happens, because a gas is going to liquid, again, bonds need to be made, and so energy is given out. So freezing and condensation are both exothermic. Because in exothermic reactions, energy is given out to the surroundings. This means that energy of the reactants is higher, and the energy of the products, hence the energy curve for the exothermic reactions, will look like this. Now let's have a look at endothermic reactions. These are less common. Remember that endothermic reactions take in energy from the surroundings. Again, as with exothermic reactions, the energy being transferred is usually heat. So in endothermic reactions, the surroundings usually get colder. Again, we can detect endothermic reactions with a thermometer because the temperature would get colder. Some examples of endothermic reactions are electrolysis, the reaction between sodium carbonate and ethanoic acid, and photosynthesis. Endothermic reactions can also be seen in physical processes. When something melts, it goes from a solid to a liquid. For this to happen, bonds need to be broken. And to break bonds, energy needs to be put in, like our melting snowman. Boiling is also endothermic because energy needs to be put in to break the bonds for the liquid to turn to gas. Because in endothermic reactions energy is added to the reaction, the energy of the products is higher than the energy of the reactants. And so the energy curve looks like this. So there you have exothermic and endothermic reactions. All you need to remember is that exothermic reactions give out energy and endothermic reactions take in energy.
In general, chemical reactions are reversible in some conditions. The energy profile diagram shows either this reaction goes forward or reverse always have activation energy. For the forward reaction, potential energy of products is higher than the reactants. More energy is absorbed by bond breaking than released during bond forming. So, overall energy is absorbed by an endothermic chemical reaction. If this reaction is to be reversed, we need to always supply enough energy to overcome the activation energy barrier. It means that reversing an endothermic reaction turns it into an exothermic reaction. Next, consider this reaction. It also can go forward or reverse reaction and always have activation energy. For the forward reaction, potential energy of the reactants is higher than the potential energy of the products. More energy is released by bond forming than absorbed during bond breaking. So, overall energy is released by an exothermic chemical reaction. If the reaction is to be reversed, we need to always supply enough energy to overcome the activation energy barrier. It means reversing an exothermic reaction turns it into an endothermic reaction. Example of questions for this subtopic. First, draw a potential energy diagram for an exothermic reaction. The term potential energy diagram is referring to energy profile diagram, which has x-axis represents progress of reaction, y-axis represents potential energy. On the graph, you must indicate potential energy of the reactants and the products. Remember, for exothermic reaction, enthalpy of reactants is higher than enthalpy of products. To indicate the activation energy for the forward reaction, we must assign from potential energy of reactant until maximum peak of the curve. To indicate the activation energy for the reverse reaction, we must identify the position of reactant and product. At the right side become reactant and the left side become product. So, the activation energy is measured from potential energy of reactant until maximum peak of the curve. The heat of the reaction is the difference between enthalpy of product and enthalpy of reactant. Next question. For the reaction A and B produce C and D, the enthalpy change of the forward reaction is positive 21 kJ per mole. The activation energy of the forward reaction is 84 kJ per mole. To sketch the reaction profile, we must think either it is endothermic reaction or exothermic reaction. The clue given here is positive 21 kJ per mole is the enthalpy change of the forward reaction. Positive value of enthalpy is referring to endothermic reaction. So, for the forward endothermic reaction, enthalpy of product is higher than the enthalpy of reactant. Given 21 kJ per mole is enthalpy change of the reaction and 84 kJ per mole is the value of activation energy for the forward reaction. So, for the reverse reaction, right side is reactant and left side is product. Thus, to evaluate the activation energy value for the reverse reaction, We must consider from the potential energy of reactant until maximum peak of the curve.